Hello there, welcome to the October 2020 paper 2. Here we're looking at question 3. A scientist is investigating the concentration of antibodies in the bloodstream of a patient following a vaccination. The concentration of antibodies X, measured in micrograms per milliliter of the blood, is modelled by the differential equation of this expression here. And find where T is the number of weeks since the vaccination was given. Find the general solution of the differential equation. So first of all, let's find the auxiliary equation for the complementary function. So it's going to be 100m squared plus 60m plus 13 equals 0. So let's go to the quadratic polynomial solver mode on our calculator. Go right down to the bottom to 100, 60 and 13. And that gives us m equals minus 0.3 plus or minus 0.2i. So therefore, x equals e to the minus 0.3 t brackets p cos 0.2 t plus q sine 0.2 t. And then for the particular solution, the particular integral, it's quite obvious that if just from observing that if x equals 2, then that will give us the 26, and then when it differentiates it just spirals out, so therefore x equals 2. So therefore the final answer therefore is x equals e to the minus 0.3 t brackets p cos 0.2 t plus q sine 0.2 t plus 2. So yeah, that's the answer for part A. Let's move on to part B. Okay, so initially there are no antibodies in the bloodstream of the patient, and the concentration of the antibodies is estimated to be increasing at 10 micrograms per milliliter per week. Find, according to the model, the maximum concentration of antibodies in the bloodstream of the patient after the vaccination. So first thing to do will probably be to use bullet point 1 and substitute in t equals 0 and x equals 0. So if we do that, we're going to get 0 equals p plus 2, because e to the power of 0 is just 1, cos to the 0 is 1, so it's p. Sine to the 0 is 0, so q gets cancelled out, and then it's plus 2, so therefore p equals minus 2. So we can now rewrite this expression here as, instead of p, we can write it with a minus 2 in there. Now the next thing to do would be to differentiate, because we want to use this piece of information here that it's increasing at 10 micrograms per milliliter per week. So let's go ahead and do that then. So it's going to be dx by dt equals, now we're going to have to differentiate this thing here using the product rule. So differentiating the first bit first, let's do that. So minus 0.3 e to the minus 0.3 t, and then it's going to be minus 2 cos 0.2 t plus q sine 0.2 t. And then leave the first one alone, differentiate the second one now. So inside the brackets differentiating now, so that's going to be plus 0.4 sine 0.2 t, and then it's going to be plus 0.2 q cos 0.2 t. Okay, let's just now group all of this stuff together. So it's going to be e to the minus 0.3 t, open brackets. So the coefficient of cos is going to be 0.6 add, is that a minus in there? No, it's a plus in there. So it's going to be 0.2 q as the coefficient of cos. And then sine is going to be minus 0.3 Q, and then plus 0.4 sine 0.2. Right, okay, so that's the answer for the differential. Now this thing here, when we substitute t equals 0, so the concentration of the antibodies is said to be increased. Oh yes, it's still initially, so still when t equals 0, we're going to have dx by dt equals 10. So let's substitute that in then. So it's going to be 10 equals, that's just going to simplify to 1 when we substitute t equals 0 in, and it's going to be 0.6 plus 0.2 q, and then this, anything to do with sine will just get cancelled out, because when you put sine of 0 you get 0. So substituting that, so rearranging this little equation here, that's going to give us 10 minus 0.6, and then times that by divide that by 0.2, and it's going to give us q equals 47. Okay, so let's now write out our equation again. So it's going to be x equals e to the minus 0.3 t, and then it's going to be minus 2 cos 0.2 t, and then it's going to be plus 47 sine 0.2 t. Sine 0.2 t. Okay, but in this question here, what we want to do then is to find, according to the model, the maximum concentration of antibodies in the bloodstream of the patient after the vaccination. So therefore, we should probably differentiate and set equal to 0, because then that will give us a maximum point. So if we now do dx by dt, now what we've got here is we've got ourselves a little shortcut to get to dx by dt if we can plug in q equals 47. So if we plug in q equals 47, then we're going to get dx by dt equals e to the minus 0.3 t brackets minus, so no, it's the coefficient of cos is going to be 10 if you plug in q equals 47, so 10 cos 0.2 t, and then on the sine is going to be minus 13.7. Minus 13.7 sine 0.2 t. Okay, so that's the differential there. Now, given that we want to find a maximum point, we'll set this thing equal to 0. So therefore, now what do we do to solve this? We can cancel out the e, because e is never equal to 0. So it's just going to be this expression inside the bracket. So therefore, it's just going to be 10 cos 0.2 t minus 13.7 sine 0.2 t equals 0. If we now rearrange this and make ourselves a tan equation, we'll move the minus 13.7 onto the other side, sine 0.2 t onto the other side, and then divide by 10, and so divide by the cos and divide by 13.7, we're going to get 10 over 13.7 equals tan 0.2 t. So we're nearly there, so let's just use this little space here. So 0.2 t is going to equal 0.2 t will equal 0.6305. 0.6305. So therefore t is going to equal 3.152. So therefore the maximum concentration in the blood, going back to the initial equation now, and substituting in t equals 3.152 using the answer button, we get x equals 12.1. And that would be 12.1 micrograms per milliliter. Whew. Okay, there we are. So that's the answer to part B then. Quite a tricky question, that one there. And we've got part C to go. So part C is a second dose of the vaccine has to be given to try to ensure that it is fully effective. It is only safe to give the second dose if the concentration of the antibodies in the bloodstream of the patient is less than 5 micrograms per milliliter. Determine whether, according to the model, it is safe to give the second dose of the vaccine to the patient exactly 10 weeks after the first dose. So if we plug in t equals 10 into the equation that we found before, the whole big equation, then we're going to get x equals 4.17, which is less than 5 micrograms per milliliter, which is less than 5 micrograms per milliliter. So yes, it is safe. So therefore, yes, it is safe. Therefore, yes, it is safe. So there we are, that's the answer for question 3 here, with 14 marks in total there. So hopefully you did well on that one. Let's now move on to question 4.